Okay, so I don't think Frank needs an introduction. So I just want to thank him for his work with Zig and for contributing not just code, but also talks like this, and like his previous one on other crypto work that he did for the Zig Standard library. So let's just give him the floor as fast as we can. The title is 25519. Yes, that's a short and enigmatic title. Frank, the stream is yours.
Hello, everyone, and welcome back. So, in the last episode, we mainly looked at symmetric cryptography, in which we had no key that was for hashing or a single secret key used for encryption and authentication. So, if we want to encrypt something for someone, we do it with a secret key. And in order to decrypt it, the recipient has to use the same key. But how do you securely share that key to start with? This is something we didn't discuss. And anytime we connect to a website using TLS, our client is able to verify that it's talking to the right server. But at the same time, the client can't pretend to be that server, which is great. So we then use encryption, but we didn't agree on a key prior to the connection. So how does that work? This all relies on asymmetric algorithms. And with this, we can prove that we know something without revealing what that is. Or we can have two or more parties compute something together, but what each party had to compute remains secret. So probably the easiest and most classic example of that is a simple Diffie-Hellman key exchange. So in this example, we have, so I think on the left it's Zigli. I don't remember the name of the other guy, so whatever, I'm just going to call him his buddy.
He's zero.
So it's zero. So this is Ziggy and zero. Okay, perfect. So Ziggy and zero wants to share some secrets. How can they do that? They need a secret key first. So what they can do is pick up a random number. So Ziggy is gonna pick some X. It could be anything, just something random, unpredictable. And zero is gonna be doing the same thing, and it's gonna have Y. This is secret. But then they're gonna share G raised to the power of their secret. So G is something that's public. It's a number, but it doesn't have to be secret. Everybody can know about it. So this is what they are going to send. And based on this, they can come up with a shared secret. So how is it going to work? This is pretty simple, actually. So 0 is going to compute G raised to the X, and this is something he got already because this is something he received. And he's going to raise that to the power of Y, his own secret. Ziggy is going to do the same thing, but using what he received and raise to its own secret. But what's pretty cool about that is that G to the Y to the X is exactly the same as G to the X to the Y. Eventually, you get exactly the same result. So this can be a shared secret. The shared secret wasn't sent explicitly. Both parties have a secret key that they never sent over the wire. They send something else that can be public. Anybody can take a look at G to the Y or G to the X. This is fine. X and Y are still secure. And based on this secret and public thing, they were somehow able to perform a computation together and come with the same result. So for that kind of thing to work, we need a function like this one. So it could be any number of parameters. But what's important here is that computing X is fast and easy. But given X, F, and just some of the parameters, finding the missing parameters is hard. So we know one of these functions already, maybe a hash function. We've been talking about that last time. So a secure hash function would satisfy the definition, but that wouldn't work for what we just did before. So if what we want is perform computations involving multiple parties, we may need something a little bit more flexible, where we can do more algebra. So if you read a paper about crypto or security proofs, you're gonna see a lot of these acronyms, DL, CDH, DDH. What does that mean? This is just a set of problems that we assume to be hard. So the first one, given that somebody knows G, so this is completely public, and G to the X, finding X is hard. This is something that we want to be hard. And a lot of constructions in cryptography depend on this problem to be hard. The CDH problem is pretty much what we did just before. So we have an attacker, a passive attacker, who knows G and both public keys, but based on that, is not able to find the shared secret. And the next one is a refinement of the previous one. Given a shared secret or some random element, an attacker is not able to tell whether this is actually the shared secret or not. So as we can see, the DDH depends on the CDH, and the CDH depends on the DL. If the discrete logarithm problem is broken, everything is going to be broken. As of today, we don't have any proofs that the DL is a hard problem in the specific context that we want it to be hard. So maybe this is not the case, but a lot of people have been looking at it, and nobody knows of an efficient way to break it. So far, so good. The only efficient way that we know is to build a large quantum computer, but then we have another hard problem, which is how to build such a large computer, and we don't really know yet. Okay, so x to the y. Well, what does it even mean? Well, this is just an operation that we recursively apply y times. Okay, so it could be pretty much anything. So assuming that this operation is a multiplication, if we just do that without context in some kind of group like all the real numbers or even all the integers, well, we have a bunch of problems. First, the result can be ginormous, and we don't want that. In computer science, we want to keep things in control in a fixed number of bits. The second problem is that this is completely insecure, because if the result is large, it means that y is large, and we don't want to disclose any information about y. So this is insecure. We need a little bit more things, more context. One thing we can do is constrain all this computation within some range. For example, in Zig, we can use a nice type like U256 and an operator that wraps around. So the first problem is solved. Now we know exactly the size that it's going to take. This is nice. Well, the problem is still completely insecure. Why is it completely insecure? Well, for example, imagine that x is just 2. Well, in this case, no matter what y is, we only have 256 possible keys. So if we want something secret, this is not great. So ideally, what we want is to have nothing that divides the size of the group. So what we want is p to be a prime number. So unfortunately, Zig doesn't have any type like this one. 2 to the 255 minus 19 is a nice number, and it's in particular a prime number. So we don't have this type yet in Zig. So we are going to implement arithmetic mod 2 to the 55 minus 19. And this number has a couple interesting properties, especially for software implementations. This is something we are going to discover. So first problem first, how do we store such a number? Because it's a pretty big number. It doesn't fit in a 64-bit register. So what we can do, pretty simple, we are going to use more registers. We are going to store 255 bits in 4 64-bit registers, or even if it's not registers, 64-bit words somewhere in memory. So that works. We even have one spare bit that we can use for anything, maybe store the sign or whatever. So this is great. Simple. Given this, how do we add two big numbers? Well, that's pretty straightforward. A0 plus B0, A1 plus B1, A2 plus B2. We can even vectorize everything. And, well, not really. I forgot something, which is a carry. Every time there is an addition, it can overflow. So we have to add the previous carry and then output a new carry for the next step. So something that looked very easy to run in parallel now becomes a very sequential operation. You have to do this carry propagation in a very specific way. Okay, whatever. How do you do a multiplication? Well, same thing. I didn't write the details. Everybody knows how to do a textbook multiplication. Other techniques exist for fast multiplications, but they share the same problems. So we compute bit 0 times A0, bit 0 times A1. Everybody meets everybody. This is great. Well, there is more. For example, every time we do a multiplication, we can have a carry. So in addition to individual multiplications, we also have additions to make with carries to propagate. Okay, so eventually we get all the lines that I didn't write here, and then we have to sum up the columns. When we sum up the columns, we still have a carry to propagate every time. So we can do everything at the same time. However, there's a problem if we only have one carry bit in the CPU. Because a CPU can be very efficient using prediction and doing multiple things at the same time if there is no conflict or dependencies. Now, if multiple instructions are competing for the same thing at the same time, performance is not going to be great. So we would need to do two completely different addition chains at the same time, but with one carry bit, it's not great. Fortunately, on recent Intel CPUs, we have a bunch of additional instructions that can use two different bits for carries. So we can actually do two addition chains at the same time. This is not too bad. However, in order to use that, first we have to use assembly. There is no way to do that directly in Zig, and it's absolutely not portable. So maybe we want to do things a little bit differently. So you got the idea. Carries are annoying. So how to get rid of the carries? One thing we could do is instead of having 4 64-bit lambs to store our 255-bit number, we can add one more. So we have 5 64-bit registers now. So now we only need 51 bits per lamb. This is nice. We have plenty of extra bits that we don't use. We don't have to use 51 bits. We can use something different, such as a bunch of limbs with 56 bits, which is nice because it's a multiple of 8. So we can use permutations or unaligned moves. We don't have to do shifts to go from a byte representation to this one. So we can use pretty much anything we want. On a 32-bit systems, we can, of course, use less bits. But the idea is to leave holes, some bits that we don't use in each of these lambs. Why is that cool? Well, now if we want to do an addition, we don't have to care about the carry. We can do all the addition in parallel. There is no overflow. And what's even better, we can do a lot of additions before it's going to overflow. So that's great. No more carries to worry about. So this is pretty nice. And what about multiplications? Well, if we want to do a multiplication, the result is going to be twice as big. Well, it could be twice as big. So what we can do is still have 5 limbs, but instead of having 64-bit limbs, we're going to use 128-bit limbs. And this is going to be very efficient. LLVM can generate very, very efficient code for that. So this is great. We just do this. And we still have 51 bits per limb. Now, for the internal multiplications, we don't have to care about the carries. There is enough space for that. So we can do all the multiplications very quickly. For the additions, same thing. We still have a lot of space. We don't have to care about the carry. So we do all these multiplications and additions, and we can benefit from some parallelism at this point. And only after we are done, we can do a carry propagation. So this is faster. However, we may still end up with a pretty large number, which is larger than 2 to the 55 minus 19. I'm just going to say p instead of 2 to the 55 minus 19. It's smaller, shorter. So yeah, we still need to make sure that we are still within the bounds, because if we do another multiplications right after, it's going to explode. So what we can do is a reduction. In this case, we have 512 bits, and we want to perform this mod p operation. So a couple techniques exist to do that. One of them is a Montgomery multiplication. You have to transform your number in a specific form, and then you can do your multiplications, and you have to transform it again. It's okay, it works pretty well. It's a very, very generic solution. There are other solutions as well. We are going to see one of them later. But another solution is to have a very nice p to start with, a very nice number. And it turns out that 2 to the 55 minus 19 is a nice number for fast reduction. And this is why. How much would be, considering these bits, 1 followed by 255 bits, which are all zeros, which is just 2 to the 55. Well, this mod p is just 19. So what we can do for the reduction is take all the bits before 2 to the 55. If we multiply that with 19, then what we get is equivalent mod p to what we had. So we just do this multiplication, and then we add the result to the lower bits, and poof, done. So this is not a complete reduction, because we have this addition. We still may overflow a little bit. However, maybe we don't care. Maybe if we still have a bunch of operations to do, a bunch of multiplication and additions, this is still very small. We can carry on. And only after we are done, we can do a full reduction, which is going to be exactly the same thing, except that we are going to do this step just one more time. So as you can see, this specific number, this 2 to the 55 minus 19 number, hasn't been picked at random. It's been specifically chosen so that implementations can be fast. Okay, so x to the n, what does that mean exactly? Exponentiation. Well, it just means that we recursively apply something n times to x. Okay, we said that already, but how do we compute an exponentiation, mod p? Well, we would do it the same way as we would it in any group. But if n is very large, we are not going to iterate n times. That would be super, super slow. So what we can do is decompose n into a sum. And then the exponentiation is just going to be a product of smaller exponentiations. So let's take a very simple example. If we want to raise x to the power of 10, there is a very simple way to decompose a number into a sum. And this is just a binary decomposition. We turn the number into binary, and we get a sum. So 10 in binary is 1010. So this is what we have on the right column. On the left, this is very simple to compute. We start with x, and we just keep squaring. So we are in a loop, and at each iteration of the loop, we square the previous result. And then we look at what we have on the right. Do we have 0? Well, we don't do anything. We don't multiply anything with numerator, which is set to 1 at the beginning, of course. And if we go to 1, then we multiply what we have with the accumulator. So eventually, we get the result much, much, much faster than having to do 10 iterations. However, as you can see, we do different things according to the different bits of the exponents. So if the exponent is some kind of secret, we can have some problems with side channels because processing a 1 is going to be slower than processing a 0. And we want to avoid side channels. So how to do that? Well, one way to do it is to use conditional moves. And rather than talking about it, I can just show you some code. We may have some right here. Let me just increase this. Okay. Do I have cmove here? Okay. So cmove is an instruction that you can find on Intel CPUs, and I think on ARM and most CPUs, you have pretty much the same kind of instructions. So what does it do? Well, it's a move, so it assigns a value to something. However, it only does it according to a third parameter. If this parameter is 0, the move doesn't happen. If the parameter is non-zero, the move happens. I was just wondering, can you see some code right now, or are you still looking at the presentation?
No, we're still looking at the presentation.
Oh, okay. That was not expected. So, okay, let me try to fix this. It will screen. Okay. What about now?
No, still presentation. Let me double check. But yeah.
You're still looking at the presentation?
Yeah. So let me think about
What?
this. It could be I think you gave permissions to Discord, right? To
I did, yeah,
yeah.
absolutely.
You know what you
Okay,
can try?
let's
You
try
can
to find.
disable screen sharing completely and restart it. So maybe that
Okay,
might fix it.
okay, no worries.
Mm-hmm.
Entire screen, go live.
Okay, now I'm
So it
seeing
should be better
everything.
now, right?
Yes. Now we see
Okay,
cmove.
that's
Yes.
okay, perfect. So cmove is an instruction that you can find on most CPUs. That just does an assignment. It stores something into a register or to memory according to a third parameter. If the parameter is 0, nothing happens. If the parameter 1, the move happens. On most CPUs, it's believed to be constant time, which is nice. However, there is no way in Zig to directly produce this specific opcode. And if we use some assembly, then the compiler doesn't know how to optimize it really well, and it's not great. So we want some generic solution to do it. And one way to do it is this trick, which is very common. We just compute the difference between here, this is FE and A. We want to store A into FE if C is 1. So we compute the difference between FE and 1. Here, this is just an XOR. And then we apply a mask. The mask is either 0 or just all 1. So if it's 0, when we apply the difference, we wouldn't be applying anything. So no changes is going to happen. Now, if the mask is -1, just 1 bit everywhere, then we apply the difference. So the move is done. So in order for this to be constant time, we rely on the fact that the compiler doesn't know how to optimize this. As of today, this is the case, and I'm not aware of any compilers that actually optimizes this, which is great. It's still a little bit scary because it may happen. However, in Zig, we ship the compiler. We know exactly what compiler we use and what version. So we can get some confidence that this is okay to do so. And so many crypto implementations depend on this, that if this assertion ever breaks, we will probably know about it. Okay, can you see the slide again?
Yes.
Okay, perfect. So this is very cool. We can do additions, multiplications, exponentiations. What about divisions now? Why not? Okay, so a division, when we divide A by B, it's equivalent to just multiplication by the inverse of B. So if we can compute an inverse, we can divide. How do we compute an inverse? By the way, what's an inverse? Well, B times the inverse of B is 1. And this is something that's very easy to figure out with real numbers. But with integers in a finite field, when we can wrap around, we can totally find a number, an inverse for B, where this works. Here's a very simple example. Using a very small row size, we are going to say that P is 31. We have 7 times 9, mod 31 equals to 1. So 9 is the inverse of 7. So we can divide even with just integers because we are in a finite field, because we can wrap around. So great, we can divide, but how do we do that? How do we compute an inverse? Well, this is a little bit complicated, but there is a very simple method, which is called the Little Fermat theorem. The demonstration is not so simple, but the result is great. So this is only valuable if P is a prime, but if we raise B to P minus 1, mod P, we get 1. So an implication of this is that the inverse of B is just B raised to P minus 2. So we know how to do an exponentiation, so we can use that to compute an inverse. But wait, we can even do something better, because P is a constant. We know what P is. So maybe we can go even faster than what we did before with the binary decomposition of the number. Let's take a look at an example. We want to compute x raised to 200. Can we do better than what we did before with squarings and this binary decomposition? Well, yeah, here's an example. This is how you can compute x raised to the power of 200. So just a few steps, and you get this result very quickly. As you can see, each step is just reusing previous results. In this case, this is reusing exactly the line before, but it could be any previous result. This is called an addition chain. It can be used to compute multiplications or for exponentiation if you just change the operators. So this is cool, but how do you find such a chain? How do you find a very small chain that would be more efficient than what we did before? It's a little bit complicated, and I don't think we have an algorithm to find optimal solutions. However, we have a couple algorithms that we can combine to find solutions that are pretty close, or even the optimal solutions. And in order to do that, some tools can help you. The one I use a lot is, it's not Zig, it's called HChain. I can maybe increase the font size if it's not too readable.
Yeah, it's pretty good.
Okay, perfect. So HChain is written in Go, but it works. Maybe we need a version in Zig. Okay, so HChain is very simple. You give it a number, and it's going to find such a chain so that you can multiply quickly with this number. So let's do it with a very concrete example. I'm going to use a different terminal, maybe. For computation, I like to use Ruby. It's a little bit weird, but I like it. So we had P equal to 2 to the 55 minus 19. This is the number we've been talking about. Pretty big number. And now let's take a look at the code. Here, if I look at the Jacobi symbol, okay. There is a technique that I'm not going to talk about to quickly check whether a number is a square or not. And in order to do so, you compute what's called the Jacobi symbol. And this is what we do. So to check that x is a square, you just raise it to p minus 1 divided by 2. Okay, so this is another case of an exponentiation that we already know about before, so we can optimize for it. So let's do it. So this is p minus 1 over 2. We want to raise to this super big number. How can we do that? Well, the traditional method probably works, but we can use an addition chain. So back to my tool, I'm going to type add chain, search this number, and wait a little bit. It's going to take a couple of seconds. Okay, so we can see a couple steps. So I don't know, maybe it takes 20 steps to achieve this super huge exponentiation. And if we take a look at the code, it's probably more readable than the description that we get from this tool. Jacobi symbol, where was it? Oh, it was right here. So this is what we do. 2 times 1, so 1 represents x. It's just the unit. So this representation right here, 2 times 1, just means that we take the unit and we square it. This is what we do in the code. Well, after we square it, we add, so we multiply. It's a plus here, but in the code, because we do exponentiation, this is a multiplication. So we multiply this square with a, and then we square it twice, and so on and so forth. So you just apply this recipe, and you get something which is sometimes way faster than using a binary decomposition. It really depends on the number. Sometimes chains can be very optimized, sometimes not so much. But yeah, for pretty much everything we have in Zig, I just use this tool, add chain, because it's nice, it works. Okay. So let's go back to the presentation. Well, where was it? Boom, 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 keynote, perfect. Perfect. We know how to do additions, multiplication, exponentiations, inversions. So we know how to divide if we want to do that. How to do square roots? Why not? Well, what is a square root? Same thing for real numbers is pretty easy to understand. But a square root is just something that when you square it, you get this something back or some equivalent. So if we are within a set of integers and we wrap around, so we have this finite field, we can probably find something that satisfies this equation. But how to find that? Well, this is complicated. There are some generate methods, and they are a little bit slow and complicated. The best one has been published just about 2 weeks ago by Sarkar. So I just put the link here. It's pretty interesting techniques. The most common one is the Tonelli-Shanks technique. These are great, but still we can do better, because for some specific primes, we can go faster. Just some. They have to satisfy something very specific so that we can apply another technique, which is just doing 1 or 2 exponentiations. So Atkin discovered that if we have p equal to 5 mod 8, then we can just do 1 exponentiation to have a square root. And it turns out that 2 to the 55 minus 19, what a surprise, satisfies this. So we can quickly perform a square root operation. This is super nice. Plus, as you can see here, this is a constant. So once again, we have to do an exponentiation using a constant so we can optimize for it. That gives us one of the roots. Once we have the positive root, we just square it to see if it works. If it doesn't, we have the negative root that can work. So to get the negative one, we just multiply by square root of minus 1. We check if it works. If it does, cool. If it doesn't, there's no solution. In either case, this is super fast, just because we have a nice prime to start with. Cool. So we can do a lot of things. Negations, I'm not going to talk about negations. This is pretty straightforward. So in mod P, we can do additions, multiplication, exponentiation, inversion, square roots, everything, even if we don't have real numbers, just because we have a finite field, and in particular, a prime field. So this is what we got, a nice prime field. Hey, remember the problems that we were trying to make hard? We just needed some context for this problem to be hard. Well, we can do exponentiations. So maybe in this context, when we do everything mod P, the problems are hard. This is why we've been doing all this, right? I got some bad news for you. Nope, it's still not secure. For that to be secure, we will need a much, much, much bigger field. Wow, why did we do that? Come on. Let me show you why. But first, let's try to do arithmetic without numbers. We've been talking about numbers too much. So, no more numbers. And we are going to take a look at vectors. So, not vectors as in Zig, but just geometric vectors. Okay, so we have one short enqueued vector. And if we take this vector and we add it to itself a couple times, we can create other vectors. So once we have other vectors, we can add them together. We can subtract vectors. We can do some kind of computations using vectors. So we know how to add vectors. What we can do is multiply two vectors together because it doesn't make any sense to multiply geometric objects with each other. But we can multiply a vector with a scalar. We can multiply a vector with a number, which is just adding it to itself a couple times. We can do that. So we're not really looking at numbers here, just pure geometry. Okay, vectors are interesting. Let's make them a little bit more interesting. But yeah, before that, we saw x to the n, and I told you before that what we did is take some operation and recursively apply it n times. But this operation can be anything. It could be a multiplication. This is what we did before. But here, we don't have multiplication. So this notation will actually mean adding x to itself n times. It's the same thing. It's just a different notation. And we could have used multiplicative notation for that. But in crypto, it's much more common to use this specific notation. But it just means that we just add x to itself n times, which works really well for vectors. Now, let's do something more interesting. We keep these vectors, but we are going to bend them a little bit to make them fit on a track, on a circle. So we have a nice circle with a start. It's nice to start from somewhere. So this is a point 0. And we still have our vectors. So now they just go on the track. So we can still do operations on that. We can still add vectors, subtract vectors. These are not really vectors anymore. What we are doing is actually more computing on angles. We are just adding and subtracting angles. But still, we can compute with that, with angles. We're not talking about numbers anymore. This is just geometric stuff. However, it doesn't seem like we are taking advantage of the geometric object itself. We are just using angles, but it could be just a number and we would get exactly the same thing. So it doesn't make the problem more complicated. So let's keep the nice circle. And we are going to define a way to do an addition slightly different. For example, we have 2 points, A and B, and we want to compute A plus B, which is going to be another point. So let's define a rule to do that. For example, one thing we can do is draw a line that goes across A and B. And then we are going to find a parallel line that crosses the starting point. and it's going to cross the circle at another point, and we are going to call this point the sum of a plus b. And this is a classic way to do an addition over conics, and that works really well. You can do a lot of additions, and you're going to jump around, but always stay on the circle. So all the points will satisfy the same equation, the equation of a circle, but still, you can do any kind of arithmetic you want. And this is pretty cool. However, this is not secure, but the idea is not too bad. So let's make it a little bit more secure. Oh, just before that, a specific case is when you want to add a point to itself. Well, in this case, you just take the tangent and you do exactly the same thing. So if you want to compute 2a, this is just a plus a. Well, you do it that way and you get the sum. So you can multiply a point using this. However, this is not secure. But if we use something pretty similar using a more interesting curve, now things can become a little bit more secure. These are elliptic curves, so different kind of curves exist with different forms for their equation. This one is probably the most classic one, if only because it's very easy to visualize how the addition works. So this is what we do. We have point A, point B, and we are going to draw a line that goes across A and B. And this line is going to come across another point on the same curve. And that point could be A plus B. However, if we do that, we have a problem. Because what would be A plus B plus A? That would be B. We would be jumping back and forth forever. This is not cool. We need to improve that. So we are going to apply a very simple tweak to that. We are just going to flip the sign of y. And then it works. We're going to get a different point every time. We are always going to get a point which is on the curve. So all the points will satisfy the same equation. And we can do additions. So if we can do additions, we can do scalar multiplications. We can do a lot of interesting things. So what we had on the slide before was some pretty cute visualization. How many points do we have? Well, on this specific visualization, we were probably using real numbers. So we have quite a lot of points, like an infinity of points. We probably don't want that. We want things to stay manageable. So what can we do? Well, what we can do is say, all right, the coordinates, x and y, are going to be integers. It's a good start. And integers in a finite field. So maybe integers between 0 and p. And then the curve looks like the background, like points all over the place. It looks like a big mess. But all these points satisfy the same curve equation. And we can still do additions exactly the same way as we did before, even if we can't visualize them really well anymore. It still works. So how many points still satisfy the equation? Of course, it depends on the curve. It depends on the equation. In Zig, right now, we have two main curves. In the Zig crypto library, we have curve 25519 and another one called Edwards 25519. You can see the equations. They are pretty short and simple, but both curves have exactly the same number of points that satisfy this equation. And this is a pretty large number. It's pretty close to 2 to the 55. It's actually bigger than that, a little bit bigger. So this is pretty cool. What we're going to do now is pick a point. So just pick a random point on the curve. And if you're lucky, actually not too much, because it's pretty easy to find a good one. What you can do with this point is add it to itself many times. Of course, you are going to stay on the curve all the time. And because we have a finite number of points, after a while, you are going to come across a point that you already saw before. So you get a loop. So how large is the set of elements that you can visit before you go back to square one? Pretty large, about 2 to the 252. So that's still pretty large. It's not 2 to the 55, but it's still really, really large. And it turns out that this number is not only large, it's also a prime number. So you know what? The problem that we are trying to make hard since the beginning, we can compute them using this new kind of way to compute. We have a prime order graph, and we can do computation on that. So that's pretty cool. And what's nice is that when you have a point, if you need to multiply it by a scalar, you pretty much have to do all the steps in order to compute it. There's no very efficient shortcut to find directly the right coordinates. Well, you can still go faster than doing all the additions, of course, but there's no super fast and super efficient shortcut to do that. And because of that, all the problems that we were trying to make hard at the beginning are now hopefully hard. Hopefully, because we don't know, but we hope that these are hard. So the benefit for that is that we can do a lot of crypto things with very small keys. Because the problem is hard, we don't need very large keys. And this is great. Now, remember, we picked a random point, and by chance, we were able to generate a graph which had this size. Now, if we pick another point, what could happen is that we can keep adding this point to itself many, many times, and we can generate a graph which is even bigger, which is not a problem. That's cool. Or if we try again and pick another point, we can just add it just to itself, because then we wrap around already, or just twice, or just 4 times, or just 8, and then we are done. So for some points, we get very, very, very small graph. This is not great, because if you receive a public key, which is within one of these graphs, and you multiply it by a shared secret, by your own secret, to generate a shared secret, well, the shared secret is not going to be very secret if you only have 8 possible values for it. So that's super dangerous. We absolutely want to avoid doing stuff in these very small graphs. And we are going to see how to do that, but not now. Let's talk about implementations of all these things. First thing first, how can we represent a point? Well, there's a very simple way to do it, using affine coordinates, x and y. Okay, so exactly like we saw on the curve, pretty straightforward. Okay, now if we have coordinates, how can we add points? Now things are very complicated. So there's a simple way to do it, which is this website. This is the Bible. This is where you have all the explicit formulas to do additions and doubling over a lot of elliptic curves. So let's take a look at this website. Oops. Because it's really cool. So it's a pretty ugly website, but it's very useful no matter what. It looks like this. So we have different kinds of elliptic curves. You can see the form of each elliptic curve. So, for example, for Edwards curve, which is Edwards to 5519 that we have in Zig, this is what the equation looks like. Could be any D right here, any A, but this is a general form of twisted Edwards curve. And the website tells you, okay, this is how to add 2 points. Maybe I can just increase the font size. This is how to add 2 points. And this is how to double a point. So how to add a point to itself. So this is pretty cool. So we can just apply that. So let's take a closer look at this. And we can see that we have divisions. And a division implies doing an inversion. And an inversion requires some exponentiation. And it's okay, but this is not the fastest operation. If we could avoiding divisions, it would be nicer. So how can we do that just to go faster? There is a very, very simple way to do it. Instead of using divisions, we are going to represent coordinates as fractions. So instead of storing x and y, we are going to store x over z and independently update x or z. If we want to divide by something, z at the beginning is 1, and we are just going to multiply z by whatever we wanted to divide x with. Multiplication is super fast. So we just maintain the denominator and the numerator independently. And only after we are done with all the computations, we actually perform the inversion to recover the real value of x. So this is much faster. We only have one inversion to do instead of having to do one every single time. So if we look again at the explicit formula database, you can see some representation for fast computations for all the kind of curves. So it's telling you stuff about extended coordinates and projective coordinates. So projective coordinates is exactly what we've been talking about. Instead of storing directly x and y, we store them as fractions. And then the formulas have been adapted to use this specific representation to be faster. And it turns out that it could be also quite efficient to keep the product of x and y around. If you have this in your set of coordinates, computations can be faster. So we have different ways to represent a point. Affine coordinates, just x and y, projective coordinates, like fractions, extended coordinates, which is the same thing, except we have a t in addition to that, which is just a product of big X and big Y. So we can take a look at the code. Still looking at this. Okay, so now this is not in field.zig. We are going to take a look at Edwards 25519 because this is what we've been talking about. And what we can look at, let me increase the font size a little bit more. And the window size, okay. Oops. For example, how can we add, this is doubling, but okay, this is how to add 2 points, for example. So that's pretty simple. And this is one of the formulas that you can find on the website before. And this is just a bunch of computations over the coordinates. Everything is mod p, but we have already written everything for that. So this is an addition. This is doubling. And you can see that a coordinate is just this, x, y, z, t. And all of them are field elements. This is an element in the 0 to the p range. So all the points are represented that way. And we do some very simple operations like this. Okay, now back to the presentation. So scalar multiplication, which is what we've been talking about before with other kind of curves, which is just starting with a point. We are going to add it to itself a couple times. So if n is really large, this is going to take forever. However, we can speed up the computation using exactly what we did before for exponentiation. We can do, for example, a binary decomposition of n, and then keep doubling p every time. So here is an example. We have a point p, and we want to compute p times 26, which is we take p and we add it to itself 26 times. 26 in binary is 1, 1, 0, 1, 0. So in a loop, we are going to compute p, 2p, 4p, 8p. So we just double it at every step of the iteration. And then if we have a bit set to 1, we are going to add it to, this is not an accumulator, this is just a point that will be moving. It starts at the origin, and then it's going to move or not according to each bit. And that's it. So this is a way to do an efficient scalar multiplication. Still, if we have n, which is like 2 to the 56 bit, we need 2 to the 56 operations. That could be a little bit slow. So in this case, we would need 255 doublings and 255 additions to complete scalar multiplication. Can we go faster? Here's a trick to go faster. What we can do is pre-compute multiples of p up to, for example, 15p. So we do that. After we have this pre-computation, what we can do is, instead of taking the bits one by one, we are going to take them 4 by 4. So this is just the beginning or the end in big endian representation of n. We are going to take the last 4 bits. And what would be the value of my points multiplied by these 4 bits? Well, we can compute this bit by bit, or we can just use what we already pre-computed. We already know everything for 4 bits because we have pre-computed everything between 0 and 15. So we just do a simple lookup, and boom, we have something for these 4 bits. What are we doing next? Well, we multiply the point by 16, just using a couple doublings, 4 doublings, and then we switch to the next set of 4 bits. And we do the same thing. We already have a pre-computation table, so we reuse it. So this is faster. And you know what? What we've been just doing is exactly the same thing as just decoding hexadecimal numbers. This is what we do when we convert an hexadecimal representation of a number to the number itself. We take things 4 bits by 4 bits, and we multiply by 16 every time. Well, we are doing exactly the same thing, using points and geometry and a bunch of random stuff underneath, but this is exactly the same thing and the same optimization. So why are we doing that? Well, because now for n up to 2 to the 56 bit, we only have 248 doublings in the main loop, and only 64 adds, plus 14 adds for the pre-computation. And some of these adds could be doublings, and doublings are a little bit faster than adds. So this is more efficient, even though we have to do some pre-computation. Hey, by the way, remember the problem that we had with this specific set of curves? Other curves don't have this problem, but these have it. That was the fact that sometimes you may end up in a very small group, and we want to reject that generally. You don't want that. If you receive a public key and it's in a small group, it doesn't smell good. You just want to send an error and not go any further. So how can we detect if we are in a small group? There is a very simple way to do it. Given the size of these groups, we multiply the points by 8. Because I don't know, if the value you get is 2, 2 times 8 mod 8 is 0. Everything mod times 8 mod 8 is going to be 0. So we can do that. Once we have finished the computation, we do a couple more computations just to multiply the result by 8. Wait, we don't need to do that because we already have a pre-computation table. We already pre-computed 8q at the beginning. So we can just check that we are not in a small group when we are doing the pre-computation. If this is the case, this is not even worth doing any more computations. We know that it stinks. So let's take a look at the code for that in Zig. And actually, I'm just going to switch to the 0.7 branch because some changes have been made recently and it's a little bit less readable. Okay, Zig and 0.7.x. Okay. So let's take a look at the code doing all this. So the pre-computation is done in a very simple way, and it could be faster by using doublings. I'm just using additions because I'm really lazy. So this is just building a pre-computation table. Very simple stuff. Oh, I'm not sure that this is the 070 branch. That code looks more complicated. Let me try to just reload the file, pre-compute. Okay, this is easier. Yeah. Okay, so same thing. We start from the identity element because this is 0. This is the first slot of the pre-computation, and then we'll just add P to itself, pre-computation table. And then how do we do the multiplication? Well, we take bits 4 by 4, and I just call this bit, which is a little bit confusing because it's multiple bits. I think I changed the name recently in another pull request, but whatever. And then if the bit is not 0, we do the addition. If not, we don't do anything. And you can see that we have two versions of this addition. This one is constant time. PC select is going to use cmove to do the lookup in the pre-computation table. And this one is just a if. Sometimes we don't care about constant time or not. For example, if you do signature verification, everything is public. So it's okay to have side channels. We don't care. There is no secrets here. Sometimes we do care. So usually we need two versions of the function, but because this is Zig, we can just use comp_time and we get two versions of the functions. Okay, so this is what we do, and then we multiply by 16 right here. Cool. Okay, we're almost done. There's a trick to make things even better, because we had a pretty large, well, not so large, 16 elements pre-computation table, but we can still process bits 4 by 4 and have a smaller pre-computation table. This is the non-adjacent form trick. So how does that work? Well, let's take a look again at the scalar that we wanted to multiply a point with. So just the n. So we have a first group of 4 bits, b0, b1, b2, b3. And this in decimal is just 10. This is just an example. And then for the next 4 bits, we get 5. Okay, cool. So now we are going to take this 10. So we start from the end, 10. And because 10 is bigger than 8, we are going to remove 16. Okay, that sounds a little bit weird at first. So we get -6. Okay. So if we multiply the points by -6, we would be totally off. To get the correct result, we need to add 16. Okay, so let's go to the next set of 4 bits. And 16 for the next set, which is like the next digit, is just 1. So essentially what we have is a carry of 1. Okay, so for the next step, we add 5, and 5 is not greater than 8. So we don't change it. We don't subtract 16. But we have a carry. So we add this carry, and we find 6. And now, this form, having -6 here and 6 here, when you perform exactly the same computations, the multiplication by 16 at every step, you get exactly the same result as with this form that we had at the beginning. This is the same thing, just a different representation. But the cool thing is that in the second form, all the coefficients are in -8 and +8. So we can have a pre-computation table that only goes up to 8p. And doing an addition or a subtraction, this is the same thing. We don't even need different pre-computation tables for that. We just need to flip a sign. So we only need a very small pre-computation table, and we can still process the number 4 bits at a time. Okay, we are almost done. Just a couple cool applications for comp_time that I found while implementing all these things. First, pre-computation tables don't have to look ugly. So let me show you what I mean by that. Remember that to generate a public key, we started with G, which was some value that both parties knew in advance. This is completely public. So we have the same thing for elliptic curves. We have a base point, which is well defined. Everybody's going to use the same. So we can already have a pre-computation table ready for this base point. This is going to make things a little bit faster if we reuse it. And traditionally in crypto libraries, you're going to find very long arrays with all the pre-computation tables hard-coded. This is super ugly. But because this is Zig, this is how the pre-computation table looks like. Where is it? This is how it looks like. We can generate everything at count time. And you know what? This is the specific thing that made me love Zig. All this 25590 thing is what I started to work on when I discovered Zig. And the file that you're looking at is one of the first things I wrote. And when I found this, wow, you can generate the pre-computation table at compile time. You don't have to hard code everything using a different program, whatever. This is amazing. So that's cool. You can pre-compute stuff that way. Another nice use case for count time that I found is in a completely different thing. So if we take a look at scalar, for example, I'm not going to talk about this. This is yet another prime field. But what's more interesting is the reduction. This is using a different technique for reduction because this is not a nice prime. So this is using a Barrett reduction, whatever. So this is still a reduction. So we have a pretty large number and we want to compute mod some prime. However, the number is not always large. Sometimes it can be 512 bits. This is the maximum we support here. But sometimes we know that it's smaller, maybe 256 bits only, or even less. The usual way to address this in an efficient way is to write different versions of the function, which are pretty much the same, actually. And what we can do using Zig is tell the compiler, this is a version for the largest size that I want to support, 512 bits, but we have some invariants. So if the lim count is on only 4, for example, I know that a bunch of parameters are going to be 0. And then the compiler is going to produce a specialized version with everything that can be optimized knowing these invariants generated automatically. I don't need a specific version of my function for different sizes. I just fix the invariants, and the compiler does multiple versions of these functions for me. And I found that really, really cool. Okay, I think we are almost done. So just another thing, I found that checked arithmetic is super useful in order to check for overflows, to check for bugs in your code, to check if you properly do carry propagations at the right time, for example. Doing that by default in debug mode is amazing. I love it. If you look at the standard library, there is std.mat.big with some really, really cool stuff to work with big numbers. This is really cool stuff, super useful stuff. However, the reason I didn't use that, well, a couple reasons. First, we want everything to be free of side channels, and this is not the purpose of std_math_big. So we need to re-implement things for crypto. Another reason is that for the specific curves, we need specific field size. We know what they are in advance, so we can do some nice optimizations that we can do with a generic implementation. Okay, once we have that, we can build a bunch of super interesting stuff. But because we are running out of time and because I want to give more talks, I'm not going to talk about actual applications of what we just saw. Sorry, but thank you.
Thank you very much, Frank. That was awesome. So let me bring up the other view. I'll bring up myself. Okay. Wow. Thank you for this talk. So it's been I had flashbacks back from university when you started talking about like curves and everything else. I think though that my
Sorry for that.
teachers, my professors didn't do as much of a good job when it came to like visualizing stuff. That was very, very interesting. So at least for me. So thank you very much. So let me think about a couple of questions. So actually, first question is: so you mentioned like this pre-computed table and how you're able to pre-compute that at compile time and everything else. So how much, like, what are, because when you said the original one had, I believe, you said you had fixed 16 elements in it, but then you were able to reduce it to 8 in certain situations, right?
Yeah, well, actually, this is all about trade-offs.
Mm-hmm.
If you want to be as fast as possible, you can compute every possible combinations
Sure.
for every single limb. Then you get a ginormous table. It's going to be super fast. This is something you can do for the base point, for example. This is something I do in libsodium, which is one of the reasons it's fast. But in Zig, we don't want a standard library with a ginormous pre-computation table because we want all this code to run well everywhere, including on small devices with not a lot of memory. So these are trade-offs. So one thing I do for that is keep the pre-computation table just to 16 elements, even if it could be bigger, especially if we know in advance the points that we are going to start from. Then we have this trick to pre-compute only 8. Well, actually 9. So if we do that, this is faster because we don't have to pre-compute as much as before. However, we have more tests to do because for every single step, we can either add or subtract. Plus, we have to put everything into this non-adjacent form before. So that has a cost. And in real-world benchmarks, I found that it was only interesting to do that, this non-adjacent form transformation, when you had a very large computation table, which is not what we have, or when you don't need constant timeness, so you can do this addition and subtractions just using a if statement instead of an equivalent, which is constant time, which is why it's only used for batch signature verifications. And then we get a small speedup. But for everything else, I still use just the 0 to 15p table.
I see.
Just based on real benchmarks. I was just talking to people on Discord. They run a bunch of benchmarks on different machines for me, which is super nice. And then I realized that it was worth it, but just on a specific case.
I see. Well, thank you. Yeah, I remember you asking people around. By the way, there's a comment by Nectro, who I'm assuming Nectro is Megan on Discord, so you can find her. If I'm
I know
mapping the name
Megan.
correctly, you can find her on Discord. So the comment is, well, I guess first of all, it's incredible talk. So yeah, I agree. And she's pointing out that the pre-computation table would only be included in the application if you compile it using the crypto algorithm. So it wouldn't be there every single time. Yeah, which I guess it's a fair point. But then if you do use this crypto algorithm, then you would have everything in the executable, and maybe that's too much for an embedded device. So the problem
Yeah,
would be there.
absolutely, especially for signatures, because even for IoT stuff, it can be pretty common to check and verify signatures. And we don't want a lot of code for IoT stuff. We want to keep things small, manageable. Maybe one thing I can do is if we compile with release small, I don't include the full table. If it's in release fast, then I can include everything. But I feel like this is a more specialized thing that should probably be in a different library rather than a standard library, and keep the standard library as lean as possible. Yeah, it's all about trade-offs.
That's a very good point, actually. Yeah, like yeah, what you just mentioned makes sense. Also, Komari Spaghetti was saying something of the sort in chat. Like you could still make that a comp time switch of some kind. But I agree that the general. There is one point which I think we haven't been discussing yet, and I think Andrew hasn't even Andrew hasn't even like precise the direction in that regard, and like what should the standard library be? And like for me personally, I agree on the point that it should be not overcomplicated. While I understand that crypto is a bit of a particular subset of things in the standard library, like for me personally, I think one of the constraints that should be considered for the standard library is that the standard library should be not too hard to understand and should show like good use of Z primitives and like it should. I think the standard library should be considered a minor resource for people learning the language, not a major one. We should not expect people to learn language by reading the standard library, but it should be one of the things that they consult. And if you overcomplicate everything for specific use cases, then you kind of make it harder for people to do that.
Yeah, I totally agree. Yeah, yeah.
Okay, so you're getting a couple more compliments in chat, but I think there are no questions because you killed everybody with all the algebra.
I try to keep things pretty light, but yeah, there was a lot of things to cover.
Yeah. No, makes total sense. So, well, I'm looking forward actually to the next talk then, when you talk about all the other stuff that was in the final slide, Ristretto and everything else. So that's cool too.
Yeah.
I don't know. So what about Kumari's question, which is, oh no, I think we covered it. Sorry, I'm reading chat and trying to make sure I don't forget anything. So I guess at this point, since I'm not in a position where I can ask you complicated questions about the discrete algebra and everything else, I'm just gonna ask you. So, how's it going? Are you enjoying yourself working in the Zig standard library? What's the best thing about it? What's the worst? Is there anything else that you want to report to the people watching?
Well, my experience so far has been really, really good. I mean, this is the main reason I keep using and enjoying using Zig so far, because crypto is something I know and like, and this is what I started to contribute. But I got some nice feedback right away, and my pull request got merged, and that was very encouraging. And I feel like, well, you can just look at how many people are contributing to Zig right now, but this is probably something that everybody's feeling. The fact that every ID seems to be welcome. And even if it's not, there are some constructive discussions every time. So this is great. This is not something where just one person controls everything. There are discussions about everything, and everybody can bring what they can to the table. And this is why the language gets better and better every day. So that's super cool, and contributing to the standard library is pretty simple because, as you said before, everything is quite simple to understand. It's not well organized yet. Things are getting better and better, but it's something that can be super useful to understand Zig first, because you have a lot of great idiomatic code in here. And then it's something that's worth contributing to, because when you contribute something here, it's going to be useful to many people. So yeah, that's cool, and everybody should do it.
So related to what you were just saying about the standard library, what is your position with regards to having a super lean standard library that only contains basically what the compiler needs plus a minimal set of features versus going for the full battery included approach? Like for you, what is a sweet spot that you think would make sense for Zig?
So having a minimal library is not that great in my opinion, because if you take a look at what happens with Rust, and Rust has a pretty nice standard library though, but even for very simple stuff, you need dependencies. You need a ton of dependencies for everything. And dependencies break, API changes. So even for very simple stuff, you spend a tremendous amount of time just trying to keep up with dependency changes. This is a waste of time. Whereas when you take a look at Go projects, of course, Go projects have some dependencies, But for a lot of very common stuff, even for HTTP, whatever, you can just use the Go standard library. So everybody is using exactly the same set of functions. So when you try to read a different project, you know how it works because everything looks familiar. Then APIs don't break, or when they break for everybody the same way. If everything is well documented, if you need documentation, everything is at the same place. Everything is maintained the same way. So having a rich standard library, in my opinion, is great because having dependencies is nice when you need something that's not very common, some very specific application. Okay, it doesn't make any sense to implement a blockchain directly in the standard library, for example. But everything that people need constantly, that should be in the standard library because having dependency is always a problem. Yeah.
Okay. Well, thank you for sharing your point of view. I think it makes sense. Like, I honestly have yet to find my personal opinion on what it should be. But one thing that I'm thinking is that going super lean, like going to the extreme of saying we just go include in the standard library what the compiler and maybe package manager needs, as if you think about it in like there's one way of looking at it is that you're basically creating a standard library optimized for writing compilers, and that's not what people should do with the
Yeah,
language. So
well, some people may be happy with that.
oh yeah, sure. So there's another I think interesting point of view. Okay, thank you very much for the talk, also for answering questions. I'm looking forward to organizing a session then where hopefully we can find a few people. As I mentioned also in the beginning of the show, you are working with Jacob and Joachim also. Well, I don't know if Joachim is tackling the code signing stuff, but Joachim is working at the very least on the AMD64 code gen. So there's a lot of effort being spent on supporting Mac, and Apple decided to throw a big wrench in everybody's plans. So on one hand, while on the other hand, it seems that the M1 architecture is amazing in many other ways. So there's always this there's always this weird combination of things. So I'm looking forward to organize some kind of like fireside chat, maybe that's a good way of describing it, where we can bring up a few people and discuss what's up. Thank you again, Frank. Is there anything else you want to say before we move forward?
Have fun.
Okay, thank you very much.
Thank you.